For our ENGI 350 project, Basil, Jake, Keith, and I worked together on the Amazon locker problem. So to help understand the problem better, we have a range of 300 customers and 30 Amazon lockers and then a distance of 30 kilometers. So for this, our C stands for customers and the number of customers range between 0 to 300 customers. And then for the Amazon lockers, L stands for lockers. But we have to at least have one locker within a 30-kilometer radius. Every locker should cover as many customers as possible within that area. But the lockers cost around 50,000 for each. For the distance, we only wanted to travel for the 30 kilometers distance because the customers do not prefer to travel more than that. But to help understand the problem, we use this method that we're going to go and select the closest locker at location XY, our coordinates X and Y, within the 30-kilometer radius. We're going to assign every customer to a locker within 30 kilometers radius randomly. And then we're going to set that new locker as an assigned locker. That means that locker is being used and it's assigned to a customer. And then we're going to mark that customer as covered. That means he is linked to a locker within that area. If all the customers are assigned to lockers within that area, we move on to the next location, our next 30-kilometer radius. We're going to repeat all these steps for every locker until we cover all the customers within that area. However, that will be our initial solution, but that will not be optimal because maybe closer customers can be assigned to closer lockers. So we wanted to improve that solution so we can have an optimal solution. But after we assigned every customer to a locker within that area, we started doing the swapping and flipping of these customers to assign them to the closest locker within that area. At the end of it, every customer assigned to a locker such that we have a minimum number of lockers assigned to a maximum number of customers. To understand that, we just wrote a very simple pseudocode where we're going to have a locker assigned, and we created a while loop. While we have a number of lockers that range between 1 to 30 lockers, and then a customers that range between 1 to 300 customers. We wanted to find the maximum distance that every locker is going to cover the maximum amount of customers. After that, we're going to assign a customer to that locker, and then we're going to create that node and name it as a current node as an occupied locker. And then our final results are going to have all the nodes which is 50,000 multiplied by the locker, and then plus the number of lockers and then customers and the distance that they traveled. But however, after that, we wanted to improve the final results, and there where we created another loop. And while we're gonna randomly select the customers to the lockers, we're gonna swap the lockers to assign every customer to the nearest locker within that area because we wanted to find the minimum number of lockers that's gonna cover the maximum number of customers. For our variables, we have decision variables. Well, XCL is going to be binary. C stands for customers, L for lockers, and then for our YL is also going to be binary, so either 0 or 1. And then for our independent variable, we have DCL. C is short for customer and L is short for location.
Next, we have our MIP formulation. We'll start with our objective function, which was to minimize the cost for each of the lockers and each of the customers that were assigned to a locker. So right here we have the summation of all 30 lockers, and it would be multiplied by 50,000 whether or not the Y decision variable was assigned for that specific locker. And then next we have the summations for the 30 lockers and the 300 customers for each of those lockers. So this is a two-dimensional variables. We have a independent distance variable and a binary assigned variable for the distances from a specific customer to a locker, and that would be multiplied by 100 for their distance to that locker. And this objective function is subject to the Y binary variable, which can either be 0 or 1, same for the X binary decision variable. And then constraint 3 is saying that all of the distances from a customer to a locker has to be less than or equal to 30 kilometers. And the fourth constraint is just saying that if a locker is assigned or not, then based on if a customer is assigned to that locker, then that locker has to at least be assigned for sure. Next, the constraints of all the customers to their lockers, each decision, which is 300 times 30, they all need to be assigned to one time. So the total needs to equal 300, as well as all of the lockers being assigned for a specific customer 1 through 300 has to equal 1, because there can only be a 1-to-1 relationship. Taking a quick look at our Excel model, we had to set up a mini model that consisted of 10 customers and 3 lockers. And so these are the binary decision variables for the X variable, and then down here we have the Y variables. And so we had to set up our constraints. We can take a look at that in Solver, and we had to set up our objective. And you can see we minimized based on these constraints and binary variables. And this is the summation of these assigned variables to customer 1 had to equal 1 because it had to be assigned to at least one locker. And then all of the lockers needed to equal 10 total lockers assigned.
And now for our IBM OPL code, as we can see here, we set our strings customers 1 through 300, excuse me. And for lockers, we set through 1 to 30 as we always do. And we have all the variables that we need for our lockers right here. And then we said that our Boolean lockers, we initialized that as our locker, and we said that this is going to be our locker and customer. And this was for this function, we wanted to minimize the sum of L in the specific locker that is going to be chosen times the 50,000, which Jake and Dina explained before, and the sum of L in locker and C in customer for the distances times 100. And these were our constraints. We said the sum L in locker, C in customer, they have to be equal to 300 because we want to serve all the 300 customers to go through a locker. And then we summed the customer, and we said it has to be equal to 1. And then we said that the customer times the distance has to be less than or equal to 30, as the constraints say. And for the last constraint that we used, the locker has to be more than or equal from the customer because we need a locker to be chosen. And this, when we run this program, our answer was 816,400 for the objective function. And we can see here, once it loads, and we can see here each customer who are assigned to what locker that is going to be used. And we can see here it's all binary as we want it to be. So customer 58 is assigned to locker 11, and so on.
So this is our Python code, coded based on the previously discussed variables and pseudocode. As you can see here on the side, there is an initial cost, and then at the end, a optimal cost, and then lists out the number of customers assigned per locker, 1 through 30 in a row here. So we base this code on a previous assignment with the simulated annealing. And to show you how it is initialized and how it actually runs through some of the heuristics here, locker is randomly assigned to a customer, and then if that is an acceptable locker, so within 30 kilometers of the customer, then it will assign that random locker to them, and that's how, for customers 1 through 300, that's how we got the initial cost there. And then it runs through the same logic, randomly assigning lockers to customers until it finds what it believes is an acceptable solution. But we believe that this is not the absolute optimal solution. It is just the one that the system was able to give us in a reasonable amount of time based on our random logic.